next we have Shaun, Principal Geologist with BHP, Copper, South Australia. He is going to talk to us about Carrapateena, evolution of data collection and storage from exploration to operating sub-level cave. Thanks.
Thanks for having me, guys. When it was suggested that I present today, my initial thoughts were, what am I going to share that may be of interest to such a broad audience? I've decided with my time today to share a quick overview of the geology of Carrapateena, talk about the different phases of drilling and studies that have occurred, and then share some low-cost ways that Carrapateena has added value to caving studies and operation by getting additional information from historical drilling. Hopefully, there'll be some small takeaways that people in the room can reflect on and can think about application to their projects. Carrapateena is 425 kilometres northwest of Adelaide and is currently an operating sub-level cave mine. Carrapateena deposit sits within the Paleoproterozoic Donington Sweet granites to the south of Olympic Dam and on the eastern edge of the Gawler Craton. Carrapateena is unconformably overlain by approximately 480 metres of Neoproterozoic sediments. Mineralisation and alteration are similar to what is observed at other large nearby South Australian IOCG deposits such as Prominent Hill and Olympic Dam. The Carrapateena geology is represented by the photos on the slides. They show increasing iron content moving from the granite through to the barren hematite breccia. As the iron content increases, so too do the sulphides, until you get to the barren hematite breccia that is relatively lacking in sulphides. The deposit geometry is generally pipe-like, with lateral extents decreasing with depth. The high-grade chalcopyrite and bornite zones have good vertical continuity of approximately a kilometre in extent. The pyrite chalcopyrite zone shows evidence of mineralisation continuing deeper than known extent of the bornite and chalcopyrite zones. The transition from the hematite breccia to the granite on the external boundaries of the deposit is generally relatively sudden, with some local zones of mineralised granite present where the mineralisation just exists in the veins. There are a variety of dikes modelled and observed. Generally, the modelled dikes are on or near the edge of mineralisation and overprint the mineralisation, indicating their relative younger age. There are zones in the breccia that have dike class and mineralisation coexisting, indicating there are some older dikes. These brecciated dikes generally lack continuity between drill holes and are often difficult to model throughout the deposit. Carrapateena was discovered in 2005 by RMG Services. They were targeting broadly coincident gravity and magnetic anomalies, with 2 drill holes partially supported by the SA government PACE program. The first hole drilled intersected dolerite with no visual mineralisation. The second hole, CAR 002, intersected significant copper mineralisation hosted within the hematite breccia. RMG then entered a JV with Teck. As part of this JV, 75,000 metres of drilling into the Carrapateena prospect needed to occur. This became phase 1 of the drilling. In 2011, Oz Minerals purchased 100% of the Carrapateena deposit from RMG and Teck. Oz Minerals continued drilling and developing the deposit through studies. This formed phase 2 of the drilling. Oz committed to a sub-level cave mine, and when the decline reached the basement and production started, so did phase 3 of the drilling. Oz Minerals was purchased by BHP in 2023 and as a result took over ownership and operation of Carrapateena. Using the phases of drilling mentioned, phase 1 in blue was all surface drilling, primarily with subvertical holes on an initial 200 by 200 metre grid pattern that was infilled in some areas to 100 by 100 metres. It was aimed to define and understand the size and large-scale grade distribution of the metal, to allow for evaluation of potential mining methods and understand the limits of the mineralisation. Phase 2 in orange was an all-surface drilling program targeting the higher grade zones defined in phase 1, but with angled and wedged surface holes from a range of azimuths to get different intercept angles. Phase 1 did a good job of understanding the lateral extents of mineralisation, but mineralisation was still open at depth, so some holes in phase 2 extended deeper to understand the potential at depth. The focus in this phase on the known high-grade zones was key to unlocking a pathway to economic extraction. Phase 3 in red has been entirely conducted from underground, primarily with sub-horizontal to -45 degree holes. This drilling has been focused on current and future mining areas. Opportunities have been taken when schedule and budget have allowed to extend these holes into areas that have known or potential mineralisation outside those future mining areas, alternate angles to the surface holes to better understand the geology. As the drilling has evolved, so has the understanding, as can be seen in this snapshot of some published models and sections of Carrapateena. For me, the major change of note in these images is as more drilling has been completed, the bornite zone in the 2010 and 2012 images has become one continuous vertical domain in the 2015 and 2024 models, and that the bornite zone highlighted in the 2006 section around the discovery hole ended up not being the main bornite zone, but a minor feature in the east. As the drilling and geology models changed through time, so too did the studies and potential mine designs. Tech looked at high-grade options like sloths, as well as bulk mining methods like block caving. Oz Minerals started with a 2-lift block cave option and then looked at high-grade options including sloths and SLC, eventually putting forward and moving into production an SLC option. The SLC was preferred, having a reduced risk profile and lower capital investment than block cave. Once the SLC was committed to and in construction, Oz then looked forward at how to expand the operation, with a study looking to transitioning block cave at depth for the lower half of the SLC. To highlight how the data and information gathering has evolved at Carrapateena, we've looked at the amount of data collected for a range of data types in each phase of drilling. The table on the left looks at the total amount of the data type and then assigns the percentage collected per phase. For example, drill meters, 32% was collected in phase 1, 29% in phase 2, and 39% in phase 3. So a relatively even distribution between phases. In terms of lead hardness measurements, this only started in phase 3, so 100% of the data is collected here. The table on the right shows for 100% of the drilling in the phase, how much of that drilling had that data collected. If we look at SG, only 32% of the drilling in phase 1 had an SG measurement. This is due to the majority of cover sequence not being measured and only every second metre in the basement, whereas SG has been collected on 78 and 83% of the drilling from phase 2 and 3 respectively. The key points of this table are the ramp-up in collection of geotechnical parameters including Q prime, RMR 89, lead hardness, mechanical test work and hydrogeological information. This aligns with the study and design phases, progressing and looking more like caving as an option. The next few slides are just some simple examples of how the Carrapateena team have continued to extract value from historic data records and samples to support this focus on caving. RQD is a commonly logged parameter. It is defined as the total length of core pieces greater than 10 centimetres divided by the total length of all core in the run. This seems like it should be able to be collected consistently across phases and between geologists, but this is not always the case. Issues can arise due to procedural drift or transfer of data between databases as some examples. It was highlighted that there were some differences in RQD between the phases of drilling, which has the potential to impact on geotechnical assessments. There was also some gaps where holes didn't have RQD collected. As all of the core has been photographed, although in slightly different methods across the phases as shown on the slide here, the photos were all taken before cutting, so preserved the breaks. They all had blocks and metre marks visible in the images, with the hole ID from and to depths visible on the trays in the photos. This historical data set of core photos allowed the team to investigate options of getting RQD from photos irrespective of the drill phase, providing one consistent data set across all drilling and filling any sections that never had it collected. At the time of this project, Oz Minerals engaged with a company called Datarock, who specialise in machine learning and artificial intelligence in the geoscience space. They reviewed the photos from over 150 kilometres of core, adapting the models to deal with the different photo types and the tray setup shown on the previous slide. They then adapted a model to segment the core and get a length measurement for each segment, identifying if it was greater than 10 centimetres or less than 10 centimetres. This then allows for the simple RQD calculation to be applied. The Datarock model also aimed to identify drillers' breaks, spun core, etc., and then could filter these out and consider the core as coherent. The comparison showed a reasonable correlation between logged and predicted RQD, but the real value was it provided data for holes that didn't initially have RQD logging and a consistent method of collection across all phases of drilling. This then allowed the subject matter experts to assess and rank logged RQD versus predicted for different phases of drilling. As studies in mining have continued, an understanding of the hydrogeology, particularly in the basement, has become more important. Early on in the life of the underground mine and drill programs, it became apparent there was basement groundwater and any potential impact needed to be understood. Water was returning to the underground drill collars from holes with several hundred metres of vertical difference between bit face and collar. The geology team started recording basic information on the drill plods and importing this information into the database, like hole depth, flow rate, pH, temperature. This was good for collecting information on the areas with new holes and building up a data set for low costs. The question was, is there anything from the historic surface holes that may help to provide information during early scoping of basement hydrogeology? The best source of information that was available was historic paper plots from the surface programs. We had scanned copies of all the drilling plots from phase 1 and phase 2 of drilling. A student geologist was tasked with reviewing all the historic plots and recording the hole ID, depth, date, shift and comment that related to water. Not the most exciting job, but a value-adding job for the team. This helped to build a picture on zones that had porosity and could impact on hydrogeology in the basement. This, combined with the information being collected and stored from the underground holes, helped to have an easily accessible preliminary data set for subject matter experts to evaluate the size and scope of work required to build a basement hydrogeology model. Based off this initial and continued data collection program, we set up a target program to collect high quality hydrogeology measurements to support a robust basement hydrogeology model to assist with future mine design. Under JORC reporting code, it is expected that sufficient evidence is retained for verification and audit purposes for publicly declared results. At Carrapateena, the majority of half-core has been retained. The majority of assay pulps has also been retained. We currently aim to retain all pulps from drilling to allow check assay work with alternate labs, mineralogy work like QXRD, and pulps can also be useful for test advances in lab techniques or different technology. The reason I've chosen to highlight effective storage is because a minor amount of our pulps were lost between phases of drilling, largely due to areas being cleaned up by non-geologists when there was no active geology on site, and weather impacting on poorly stored samples. To help facilitate better storage, the team set about a low-cost and effective way, so we use 40-foot shipping containers with shelving pre-installed before we get them, with each container able to fit 60,000 pulps. This is often an effective, cost-effective solution for us on site. I know this talk wasn't groundbreaking, but hopefully it might create a little thought in people's heads about how your deposits or mines might evolve through different mining technique studies and what types of data you may be required to support them. Are you storing as much information as practical in a central database, not just assay and logging, but anything related to the core and the drill hole itself? You never know how it might be used in the future as technology and mining changes. Are the photos being taken in a way that can be utilised by future geologists and potentially machine learning? Are the physical core and pulps being preserved as well as practical? Not all the solutions are labour intensive or cost prohibitive. The geologists in the field spend the most time planning, looking and collating the data from drilling. People back in the office, geotechs, other professionals, they don't get to see what's different. The geos in the field are the ones that pick up on those differences, and having the ability to note them down and record that is what's going to provide value to people in the future. So do what you can to record as much as possible. You never know when it will be useful. Thank you.